Okay, let's take a look at problem 1. So we have a normal distribution with a population mean of 5.7 and a population standard deviation of 1.5. Since it's a normal distribution, we can just draw the bell curve, and we have our population mean and population standard deviation. No samples have been taken. We're just asking about the probability of one student, or we could ask what proportion of students generally. We want to know the probability that a student revises his or her paper less than 5 times. So we're going to draw a bell curve with a population mean of 5.7 and a population standard deviation of 1.5. Note that I've labeled the axis with x. That's our random variable, x, number of times that the paper is revised. So since we're interested in the probability that the number is less than 5, we're going to shade that area. Then we're going to compute the number of standard deviations between 5 and the population mean of 5.7. It's the area here between the arrows. And so we've got x minus mu over sigma, or 5 minus 5.7 over 1.5. That's minus 0.47. That means we're not quite 1/2 standard deviation below the population mean. So we're going to look up that 0.47. Let me go back and say that the negative 0.47 just means that we're below the mean. And so in the table, we're just going to look up 0.47 and we get 1808. That's the area between 5 and 5.7, between the value x and the mean 5.7. Of course, we're not interested in that area. We're interested in the area that's shaded blue. So we're going to subtract that 0.108 from 5 and get 0.3192. Okay, so for part B, we want to know the probability that we get between 7 and 9. So we still have our bell curve. Now we're going to shade the area from 7 to 9. And so what we can do is we can calculate the two areas I kind of have designated here from 5.7 to 9 and also from 5.7 to 7. We can't go directly there because we can only calculate from the mean to some point. So for area A here, we're going to compute between 9 and 5.7 and then find the corresponding probability. So 9 minus 5.7 divided by 1.5 is 2.2, and that's going to give you 0.4861. Just a minor note here, 5 or 6 people that took this test actually looked up the value for 2.02. And we're just in that first column there, 2.20. You should get 4861. And then we're going to get the area between 7 and 5.7 and find that area. So 7 minus 5.7 over 1.5 is 0.87. If you look that up in the table, you should get 0.3078. Then, just looking at the picture, you should be able to see that we're just going to get the difference between these two areas designated by the arrows, and that's going to give us the area that we have shaded in blue, which is the area we're after. And that's 1783. Just a reminder here, z-values are associated with the distance from the mean. So all calculations go from some point to the mean. So in this particular problem, we can't go from 7 to 9, but we can find from the mean, 5.7 to 7, and from the mean to 9, or 9 minus 5.7. Okay, for part C, we want to find the 80th percentile. Again, draw the bell curve. Now we're going to designate, in this case I've just shaded in an area that's about 80%. You might just want to draw a line there and draw arrows. But at any rate, I've somehow designated an area that's about 80%. Well, 50% of that area is below the mean. So from 5.7 down, we've got 0.5. That means that the area between 5.7 and wherever the 80th percentile is 0.3. That's just the 80% minus 50%, or 0.8 minus 0.5. Now, what you need to know about this when we're looking at percentiles is basically we're going to go backwards. Previously, we computed a z-value, number of standard deviations from the mean, and then used that z-value to look up a probability in the z-table. Percentile problems, we start with a probability, in this case 0.3 or 30%. That's the percentage of values between the mean and in this case the 80th percentile. Now we're going to go to the center of the z-table and find a value or a probability that's close to 0.3. The closest is 0.2995. I'll show you that on the next slide. But once you get to that 2995, you're going to work your way out to a z-value. You'll see that on the next slide as well. So here we are with a portion of the z-table here. And you can see that the closest number to 0.3 is 0.2995. And that if you back your way out to a z-value, it's at 0.84. So what that means is the 80th percentile is 0.84 standard deviations above the mean, not quite one standard deviation above the mean. So that value there, we'll just call it x, is going to be the 80th percentile, and we know that it's 0.84 standard deviations above the mean. So we can just take the mean and add 0.84 standard deviations, or mu plus z times sigma. So 5.7 plus 0.84 standard deviations, which is 1.5. Work that all out and you'll get 6.96. And so about 80% of values are below 6.96. Part D now. We still have the normal distribution and a population mean of 5.7 and a population standard deviation of 1.5. But now the question's different, and so is the data. We have a random sample of 9 students, so now we have a sample that's been taken, whereas before we did not. And we're going to find the probability that a sample mean number of revisions is less than 5. We're not asking about an individual number, an individual student. We're not asking about an individual number or an individual student, or we're not asking about what proportion of all students. We're looking at the sample mean, and the probability that the sample mean is less than 5. So we're looking at a sampling distribution now, and you can tell, because we've taken a sample, n is equal to 9, and because the question involves a sample mean. Now what that means is we're going to have to change the labels. The random variable is now x bar, not x. And you have to calculate the standard error, in this case by dividing the standard deviation by the square root of n. Now in this particular case, we had to know that the population was normal because we have a small sample size, n is equal to 9. For larger samples, we wouldn't have to know the shape of the population. Okay, so here's what I mean by change the labels. On the axis, we have x bar, and our mean now is the mu of the x bars, and the standard error of the x bars is equal to the population standard deviation divided by the square root of n, or 1.5 divided by the square root of 9, which is 0.5. Now we're going to shade the area of interest. That is, we want to know the probability of finding an x bar, a sample mean, that's less than 5. So we're going to compute the probability from the mean, that's 5.7, to 5, or the sample mean. I should say compute the probability from the population mean, or from the mean of the sampling distribution, which is the same thing, that's 5.7, to 5, which is the sample mean in this particular sample. So we've got a z-value is the random variable x bar minus the mean of the distribution, which is mu x bar, divided by the standard deviation, or in this case the standard error of the sampling distribution. That'll comes out to be minus 1.4. And again, like before, I had some people, when they looked up the probability, they looked it up for 1.04 instead of 1.40. Well, anyway, for 1.40, it's 0.4192. That's from 5 to the mean. So to get the area of interest, we're going to get the area in the tail by subtracting that 4192 from 0.5. That comes out to be 0.0808.